What if a fuel and an oxidizer burst into flame the moment they touch? That's what hypergolic propellants do. They ignite spontaneously on contact, with no spark or igniter needed. That instant ignition makes them extremely reliable for precise rocket maneuvers and engine restarts, useful for satellites and spacecraft during orbital adjustments. For decades, engineers used hydrazine-based fuels because they work well. The problem is hydrazine is highly toxic and dangerous to handle, so researchers have been looking for safer alternatives. One promising alternative is ionic liquids, which are designer salts that are liquid at room temperature. These can have very low vapor pressures and be tuned by chemists to balance performance and safety. They don't evaporate easily and can be made less hazardous than traditional fuels. Designing a good hypergolic propellant is all about balancing different properties. Engineers look at ignition delay, which is the tiny fraction of time between contact and ignition. The shorter it is, the more reliable the engine starts. They also measure how much energy the fuel can deliver, known as specific impulse, and how stable it stays over time, which affects how safely it can be stored. But every improvement comes with a trade-off. For example, a highly energetic fuel might be harder to store safely. Additionally, additives like nanoparticles can help the reaction start faster, but they can also make the mixture clump or behave unpredictably. Balancing these factors is what makes designing a hypergolic propellant such a careful, delicate process. Even with safer designs, this chemistry remains hazardous. It takes strict safety systems and trained professionals. It's not something to experiment with outside of a lab. Hypergolics may look simple, just two liquids that ignite on contact, but behind that instant flash lies decades of research, fine-tuning, and trade-offs that make spaceflight possible.